Hi everyone, welcome to my channel and I'm glad to see you again. In statistical modeling, regression analysis is a set of statistical processes for estimating the relationship between dependent and independent variables. In this video, I'll be demonstrating how to perform multiple linear regression analysis in SPSS. Please endeavor to see this video to the end. My name is Titocan and this is Titocan Solutions, a YouTube channel for improving the knowledge of how to do things. If you have not subscribed to this channel, please kindly do so now by clicking on the red subscribe button, and by doing so, you have encouraged education and learning. Multiple linear regression analysis is a statistical technique that uses two or more explanatory variables to predict the outcome of a response variable. That is, multiple linear regression is a statistical procedure which consists the use of two or more independent variables in a linear fashion to produce a model that predicts the response or dependent variable. And this procedure is similar to the method of ordinary least square and is made easy in SPSS. The equation for multiple linear regression model is typically expressed as this, where y is the dependent variable or the response variable, xp is the independent variables or the predictors, mp is the slope coefficients for each independent variable or predictor, b0 is the constant term or the y-intercept, and e is the residual or model error term, but usually negligible in practical terms. Our simple requirement in performing multiple linear regression analysis is to determine the value of the constant term, which is the y-intercept, and the values of the slope coefficient for each independent variable or predictor in the equation, so that it becomes a useful model. However, there are some assumptions your dataset of variables must satisfy in order for the model output to be valid. The assumptions are: 1. Your dependent variable should be measured on a continuous scale. That is, it should either be interval or ratio variable. You can test this assumption by direct data inspection. 2. Your data must include two or more independent variables, which can be either continuous or categorical variables. Continuous data are interval or ratio variable, while categorical data are ordinal or nominal variable. You can test this assumption by direct data inspections too. 3. Your data should have independence of observations, and you can test this assumption by using W-Watson statistic. 4. There should be a linear relationship between the dependent variable and each of your independent variables. And you can test this assumption graphically by using partial regression plots. 5. Your data should exhibit homoscedasticity, which means the variances in your data should remain similar, constant, and elliptical. You can test for this assumption by using partial regression plot or by making a scatter plot of regression standardized residual against regression standardized predicted value. 6. There should be no multicollinearity among your independent variables, so as to avoid the inability of determining which independent variable contributes to the variance explained in the dependent variable. You can test this assumption by using collinearity statistics, which include tolerance and variance inflation factor or VIF. 7. There should be no significant outliers in order to protect the residual and make the prediction outcome valid. And you can test this assumption by using case-wise diagnostics. And 8. The residual or errors of the regression line should be approximately normally distributed. You can test this assumption by using histogram with a superimposed normal curve and the normal PP plots. If any of these assumptions is violated or not met by your data, the results of the multiple linear regression analysis may not be valid. In this case, you may have to go back into your dataset and do some corrections where necessary, and then return to perform the regression analysis. On the other hand, you may be required to perform a nonlinear regression analysis should your data be badly conditioned. So, it is important to test your data for these assumptions and ensure they are tenable before you progress to assess the regression results or use the model. Now, let's take a look at the data for this demonstration. This is our set of fictitious data created for the purpose of this demonstration. The data represents the wish of an employer to determine or predict the impacts on the job when a staff is sad, obsessed, or being enhanced. The data is already loaded into SPSS and it consists of 3 independent variables, which include sadness, obsession, and enhancement, while the dependent variable is impacts. The sample size or the number of cases for this dataset is 100 for each variable. However, if you have data as small as 20 cases for each variable, you can still perform multiple linear regression analysis provided the dependent or response variable is normally distributed. Now, let's go into SPSS and get started with the demonstration. But first, let's be sure this data satisfies all the required assumptions by putting the dataset to test of assumptions. The test of assumption number 1 and 2 can be determined by mere inspection of the raw dataset, while the assumption number 3 to 8 will be performed simultaneously with the regression analysis procedure. So, assumption number 1 is simple to test. As you can see, the dependent variable impacts is a continuous scale variable measured at interval level, which satisfies assumption number 1. Assumption number 2 is also simple to test. As you can see, there are 3 independent variables: sadness, obsession, and enhancement. They are all continuous scale variables, and this satisfies the assumption number 2. However, one of your independent variables or predictors can be a categorical variable, especially one that is dichotomous, such as gender, and the multiple linear regression analysis will just still work fine. So now, we will go into the regression procedure to perform the multiple linear regression analysis and simultaneously perform the remaining tests of assumptions. Now, go to the menu bar and click on Analyze. From the sub-menu, put your cursor on Regression, and from the drop-down options, click on Linear, and the Linear Regression dialog box opens. In this dialog box, you have your data in the box on the left. At the upper right corner, there are 2 relevant boxes, that is the dependent box and the independent box. In this video, I want to use the sadness, the obsession, and the enhancement as predictors or independent variables to predict the impacts as response or dependent variable. So, I click on the independent variable, sadness, hold down the Shift key, and click on Enhancement to select all the 3 independent variables. And then click on this transfer arrow key to move them to the independent box. Thereafter, I click on the dependent variable, impacts, and then click on this transfer arrow key to move it to the dependent box. Leave the method option as Enter, which is the default name given by SPSS Statistics for standard regression analysis. At this point, you can click OK and the multiple linear regression result will be produced in the output window. But there is need to make additional selection of statistics and plots in order to verify the size of our data and to also test for the remaining assumptions. So, click on the Statistics button to open the Linear Regression Statistics dialog box. In this dialog box, the estimates and the model fit boxes have already been checked by default. In addition, check the box for confidence interval and ensure the level is set at 95%. This selection will produce the 95% confidence interval for the model output or for the coefficients of the variables. Then, check off the box for arrow squared change. This selection will produce a test statistic in the model summary table that quantify whether the arrow square or the variance explained in the dependent variable is significant or not. This option is very important, especially if you want to be sure you are doing the right thing. Now, check the box for descriptives. This selection will produce a table of the mean, the standard deviation, and the sample size of the variables as the first list of table in the output window. Now, check the box for collinearity diagnostics. This selection will produce a table of collinearity diagnostics and columns of collinearity statistics in the coefficient table, which will include the tolerance and the variance inflation factor VIF that will be used to test for assumption number 6, which is the issue of multicollinearity among independent variables. Then check the box for Dobbin waxing. This selection will be used to test for assumption number 3, which is the issue of independence of observations. The Dobbin waxing statistics result will be presented as the last column in the model summary table. Next, check the box for case-wise diagnostics. This selection will be used to test assumption number 7, which is an issue of outliers. This selection will generate case-wise diagnostic table and the residual statistics table that can be used to check for outliers. Please note that if there is outlier in your dataset, this selection will produce a case-wise diagnostic table containing list of cases of outliers. But if there is no outlier in your dataset, the case-wise diagnostic table will not be produced. After you have checked the necessary boxes like I have done, then click Continue to close this dialog box. Now click on the plus button to open the Linear Regression Plus dialog box. In this dialog box, transfer the zpredict written as zpred to the X box, and then transfer the zresidual written as zresid to the Y box. This selection will produce a scatter plot that will be used to assess assumption number 5, which is an issue of homoscedasticity. You should expect the scatter plot to exhibit zero pattern. Next, check the box for Produce all partial plots. This selection will produce several partial regression plots of the dependent variable and each of the independent variables that will be used to test assumption number 4, which is the issue of linear relationship. Then, check the box for histogram, and this selection will produce a histogram with a superimposed normal curve. This plot will be used to test assumption number 8, which has to do with the issue of approximately normally distributed residuals. Next, check the box for normal probability plot. This plot selection will produce a normal PP plot of regression standardized residual, and this plot will be used as added on to test for assumption number 8, which has to do with the issue of approximately normally distributed residual. Then click Continue to close this dialog box. For record purposes, click on the Save button. In this dialog box, please note that some authors and statisticians may check off cooks as addendum of checking for outliers. But for this tutorial, I will uncheck the box and move on since we have the case-wise diagnostics, which I have already checked off in the statistics section. There is no further configuration to do in the other buttons, so this procedure has been configured for multiple linear regression analysis. And then click OK to produce the multiple linear regression results in the output window. Now, before we proceed to interpret the results, let's check whether the data satisfied the remaining number 3 to 8 assumptions. The test for independence of observations, which is assumption number 3, was performed using the Dubbin-Watson's test statistics. Now, proceed to the model summary table to see the Dubbin-Watson's test. Here, as you can see, the Dubbin-Watson's test result is 1.993. Generally, for independence of observations, the Dubbin-Watson's test result should not be less than 1 or greater than 3. As you can see, 1.993 is neither less than 1 nor greater than 3. So this means the assumption number 3 is tenable because the data has independence of observations. For assumption number 4, we used partial regression plots to test for linear relationship. Now let's proceed to the partial regression plots. This first partial regression plot is a scatter plot of the dependent variable impacts against the independent variable sadness. To clearly determine whether there is a linear relationship between them, let's insert a regression line. To do that, double-click anywhere on the scatter plot. Then go to the first two bars on the chart editor and click on Add Fit Line at Total. Then close the chart editor. As you can see, there is a negative linear relationship between the dependent variable impacts and the independent variable sadness. That means there will be decrease in impact on the job at every unit increase in sadness. This relationship can also be true in real life. When one is sad on the job, one can hardly be productive. But this relationship also showed that the data exhibit homoscedasticity because the variance above and below the regression line is constant along the line. Now, let's scroll to the next scatter plot. This second partial regression plot is a scatter plot of the dependent variable impacts against the independent variable obsession. Again, let's insert the regression line. As you can see, there is a positive linear relationship between the dependent variable impacts and the independent variable obsession. That means there will be increase in impacts on the job at every unit increase in obsession. This relationship also shows that the data exhibit homoscedasticity because the variance above and below the regression line is constant along the line. Now, let's scroll to the next scatter plot. This third partial regression plot is a scatter plot of the dependent variable impacts against the independent variable enhancement. Again, let's insert the regression line. As you can see, there is a positive linear relationship between the dependent variable impacts and the independent variable enhancement. That means there will be increase in impacts on the job at every unit increase in enhancement. This relationship also shows that the data exhibits homoscedasticity because the variance above and below the regression line is constant along the line. For issue of homoscedasticity, which is the assumption number 5, we also use the scatter plot of the standardized predicted value against the standardized residual value to check whether the data exhibit homoscedasticity as required by regression analysis. Now, let's proceed to the scatter plots. This is the scatter plot of the regression standardized predicted value against the regression standardized residual value. As usual, let's insert a regression line. As you can see, this scatter plot has zero pattern or relationship as expected. It is elliptical and therefore the size of the residual and the variances along the line of best fit remain similar above and below, and the dots did not go beyond the extremes of the x and y axis respectively. So the data exhibit homoscedasticity. If your scatter plot is not similar to this, then your data exhibit heteroscedasticity, which will mean something is wrong with your dataset. And so you cannot use the data for multiple linear regression analysis. But our data here exhibit homoscedasticity, and we are therefore good to go. Assumption number 6 is the issue of multicollinearity among the independent variables, and this was tested by using tolerance and variance inflation factor VIF, produced by checking off the collinearity diagnostic box in the statistics section. Now, let's proceed to the coefficient table to check for tolerance and variance inflation factor VIF. This is the tolerance and VIF column under the collinearity statistics in this coefficient table. Though the collinearity diagnostic table is also produced, we will concentrate only on the tolerance and VIF in the coefficient table because their interpretation points in the same direction. In the collinearity statistics column, the tolerance should not be less than 0.1 and the VIF should not be greater than 10. As you can see, for the independent variables, the tolerance is 0.816 for sadness, 0.672 for obsession, and 0.766 for enhancement, while the VIF is 1.225 for sadness, 1.489 for obsession, and 1.305 for enhancement. This means there is no issue of multicollinearity among the predictors or independent variables. So the assumption number 6 is tenable or satisfied. And if you proceed to the correlation matrix table, you will see that all the independent variables are not highly correlated among themselves. Assumption number 7 is the issue of significant outliers, and we tested this assumption by using case-wise diagnostics. Now, let's proceed to find the case-wise diagnostic table. There is no such table produced in this output window. That means there is no outliers in this dataset. But to be sure there is truly no outliers, let's proceed to the residual statistics table. Here in the residual statistics table, we will focus only on the minimal and maximal standardized residual. Generally, the minimal standardized residual should not be less than -3.29 and the maximal standardized residual should not be greater than +3.29. If they do, then there is outlier in your dataset. But here in this table, the minimal standardized residual is -2.289, which is greater than -3.29, while the maximal standardized residual is +2.524, which is less than +3.29. This means there is truly no outliers in this dataset, and that was why the case-wise diagnostic table is not produced. This means assumption number 7 is satisfied and tenable. Assumption number 8, which is the issue of approximately normally distributed residual, was tested by using the histogram and the normal probability plot or the normal PP plot. Now, let's proceed to the histogram and the PP plot. As you can see, the histogram and the superimposed normal curve look like a bell shape, which is what we'll expect to see for a normally distributed dataset. But to conclude that the residual is normally distributed, we need to look at the normal PP plot of the regression standardized residual. As you can see, the dots on the PP plot are closely distributed along the 45 degrees fitted line, but not exactly along the straight line. This shows that the residual is approximately normally distributed. Suffice to say, the assumption number 8 is satisfied and tenable. So all the assumptions have been met. There is nothing to transform or fix in this dataset. So the data is qualified to be used for multiple linear regression analysis. Now we can proceed to interpret the result output. Let's proceed to the first table. The first table here is the descriptive statistics. This table gives idea of the mean, the standard deviation, and the number of cases of the variables. Such information is important to be known. For each of the variable, there are 100 number of cases. The second table is the correlation matrix table. The Pearson's correlation coefficient shows that the variables exhibit relatively strong correlation between and among themselves. This also improves the knowledge of the linear relationship between and among the variables. The third table is the variable entered or removed. This table tells us the number of predictors in the regression model. Here, the only predictor in the model are enhancement, sadness, and obsession, applied as enter method, and the dependent or response variable is impact, which confirms that we are performing multiple linear regression analysis. Please take note of the subscript A and B. The fourth table is the model summary table. In this table, there are some useful information. Here, the important columns are the arrow column, the arrow square column, and the sig-f change column, also called the p-value column. The arrow, which is the Pearson's correlation coefficient, is given as 0.483, and this is relative to the predictors or independent variables. This means the predictors or the independent variables put together produced a correlation coefficient of 0.483, which is fairly strong correlation. But we don't know as of now which among the predictors or the independent variables is contributing more or less. We will find that soon. Then the arrow square, called the coefficient of determination, which is the proportion of the variability in the outcome variable accounted for by the predictor variable. The arrow square is given as 0.233, and since it is interpreted in percentage, we multiply it by 100, and this gives us 23.3, which means 23.3% of the variance in impact on the job is predicted from the independent variables. This seems to be a small amount of variance, but the p-value here in the sig-f change column shows that the 23.3% variance in impact on the job is significant from the predictors. But as of now, we don't know how many predictors are significantly contributing to this variability. However, you can use the adjusted arrow, especially if you have small data size, to mean the same thing. The fifth table is the ANOVA table, and the ANOVA result is presented here to tell us whether the model works or not by indicating whether the predictors put together are significant or not. That is, it indicates whether the model with the three predictors significantly works better than just using their mean values. As you can see in the ANOVA table, the significance level or the p-value, which is designated as xig, is 0.000, which is less than 0.05. This means the predictors are significant and the model works. Now we can proceed to the sixth table, which is the coefficient table. This is a very important table in regression analysis because this table tells us how the model works. Remember, the typical model equation is given as this, which when rewritten according to the variables in this tutorial would be impact equals B plus M1 multiplied by sadness plus M2 multiplied by obsession plus M3 multiplied by enhancement, since this data has only three predictors or independent variables at negligible error. Here in this equation, B is the constant term or the y-intercept, and M1, M2, and M3 are the coefficient values of the predictors. So this table provides the constant term and the coefficient values. So our main concern in this table is the column B under the unstandardized coefficients. As you can see, the constant value under the column B is 24.006, while the sadness coefficient value M1 is minus 0.096. The obsession coefficient value M2 is 0.268, and the enhancement coefficient value M3 is 0.350. But at this point, you must check whether the three independent variables or predictors are significantly contributing to the model or to the dependent or response variable. To check for this, you look at their p-values under the significance level column or the sig column. The predictor variables will be agreed to be making significant contribution if and only if the p-value is less than 0.05. So, any predictor whose p-value is greater than 0.05 can be said not to be making any useful contribution and so can be removed from the model as a predictor. So, as you can see in this sig column, the p-value of sadness is 0.380, which is greater than 0.05, while the p-value of obsession is 0.024 and the p-value of enhancement is 0.001, which is less than 0.05 respectively. This means the obsession and the enhancement variables are the only predictors that are significantly contributing to the model to increase the impact on the job. The sadness variable is not yielding any impact to the job. So we will remove sadness as a predictor in the model so that we will now have only two variables, obsession and enhancement, as our predictors. That is, our model equation will now reduce to impact equals B plus M2 multiplied by obsession plus M3 multiplied by enhancement. When you fix the coefficient values into the regression model, you will now have impact equals 24.006 plus 0.268 multiplied by obsession plus 0.350 multiplied by enhancement. This model means for every 1 unit increase in obsession and enhancement, the impact on the job will increase by 0.268 and 0.350 respectively. Another important column in this coefficient table is the beta column under the standardized coefficients. The values here tell us how much contribution each variable predictor is making to the model. As you can see, enhancement is making the highest contribution of 0.340 to the model, followed by obsession making a contribution of 0.250, while sadness is making no contribution at all because it has negative value. However, the 95% confidence interval for the unstandardized coefficient B shows the lower and upper bound of the range of units each predictor can make in relation to the negligible error associated. Now, since we have our coefficients, let's now use our regression model to make predictions as required. Let's predict the impact on a job if 1. Obsession is 15% and enhancement is 25%. And 2. If obsession is 35% and enhancement is 12%. The way to apply the model is to substitute for obsession and enhancement in the equation their values as appropriate. Your result will be as highlighted in the table. That is, at obsession equals 15% and enhancement equals 25%, the impact on the job would be 36.78%. And at obsession equals 35% and enhancement equals 12%, the impact on the job will be 37.59%. This is how to perform multiple linear regression analysis in SPSS. If you have any question, please leave it with me at the comment section. But right now, we have come to the end of this video, and I hope you will be able to replicate the procedure as demonstrated in this video to perform multiple linear regression analysis of your data in SPSS. If you like this video and you want to see more video content like this, please give this video a thumbs up and please subscribe to my YouTube channel so that we begin to send you notification every time I publish new and useful content. Subscription is free. Thanks for your time and subscription, and I hope to see you again in my next video. Bye.